Okay, great. Another question from Sean. I really appreciate it, buddy. So here's the initial situation. You got two electrons. Their masses are easily looked up. And we're going to assume that they're being shot at each other, so they're really far apart. So the distance between them, center to center, is basically infinity. And this is how each of them have the common speed as they're being shot towards each other. So that's known VI. Then what happens is they're going to start to approach each other. They're going to get closer and closer and closer and closer and closer. But they're going to get to a point where the repulsion is so strong that they'll stop. And we want to find out how far apart they are from each other when they stop. So once again, we're going to use the law of conservation of energy to figure this out. Total energy initial is equal to total energy final. And then we know that the energies that we're dealing with here are kinetic and electric potential, both in the initial and final situations. But the initial electric potential energy is zero. They're so far apart from each other, there's no electric potential energy. And the final kinetic energy is zero. They stop when they get as close as they possibly can to each other. So we're going to put in the equation for kinetic energy, half mass of the electron times its initial speed squared. But remember, there's two electrons, is equal to the electric potential energy between them, K, charge electron divided by the value we're trying to find. How far apart are they? 2 times a half is gone, gives us 1. So mass, initial speed squared is equal to K Q squared. They're the same quantity, square them all over RF. We do a little fancy rearranging. We bring the RF up and the MVI squared down. Little switcheroo there. And there's your equation for the final distance between the electrons that were shot at each other. Thanks for asking the question. Appreciate it. Bye-bye.